Alright, in this video we're going to be looking at transformers. Let's start with a little bit of history. A man by the name of Michael Faraday did a lot of work with electricity and magnetism and how they relate to one another. One of his experiments actually showed that if you have a alternating current in one circuit, you could create a current in a separate circuit nearby. And the experiment looked something like this. This isn't going to be exactly the same, but it's close enough. He had an iron ring, and on one side he had a coil of wire hooked up to a source of alternating current. On the other side he had another coil hooked up to some sort of load, whether it was a galvanometer to measure voltage or current, or maybe it was a light bulb. I'm going to draw a light bulb here. But he had something to tell whether current was being induced in the other circuit or not. Now, this right here that I drew, the circle with the squiggle in it, represents a source of alternating current. And he found that this alternating current created a magnetic field in this coil. And because the current alternated, so did the magnetic field. So the magnetic field kept switching back and forth in this circuit. Now, in the last, in one of the earlier sections, we talked about ways you can induce current. One of the ways you can induce current is with a changing magnetic field. So as this magnetic field changed, it created a current in this other coil. And this is what we call mutual inductance. So inducing this magnetic field induces this current. Now, what I've drawn here is actually a simple transformer. A transformer consists of two coils of wire wrapped around an iron core. Now, the coil on the side connected to your voltage source is called the primary coil. The other coil is called the secondary coil. And there's two types of transformers. And I do not mean Autobots and Decepticons. The two types of transformers are step-up and step-down transformers. Now, if your secondary coil, the one on your output side, has more loops than your primary coil, it is a step-up transformer. So, for instance, the transformer I drew here is a step-up transformer. The side hooked up to your voltage source in this, or a current source, is your primary coil. The other coil is your secondary. And the way I drew mine, the secondary coil has more loops in it. So it's a step-up transformer. Now, if your primary coil has more loops than the secondary, then it's a step-down transformer. Now, the purpose of a transformer is to basically change your voltage. If you've ever been overseas, you've probably noticed or probably know that if you have like a hair dryer or some other appliance that you have to plug in, maybe it's your phone charger, you can't just plug your stuff into the outlets overseas, not necessarily, because some of them, their outlets are different, but sometimes it's more because the amount of voltage supplied is different. In the United States, our current alternates at a rate of 60 Hertz, and we get about 120 volts out of our outlets. That's not the same in every country. So if you go to another country, you might find that you have to have an adapter. That adapter is actually a transformer. It's either going to increase or decrease the current that to make it what you need for your appliance. So a step-up transformer would increase the voltage from your source. A step-down transformer would decrease the voltage from the source. Now, in both types of transformers, your electrical power does not change. Now, electrical power, remember, is your current times your voltage. So if power is staying the same, but you increase your voltage, current has to go down. Or if you decrease your voltage, current would have to go up. But in both cases, power is going to stay the same. Now, real transformers are not 100% efficient. Normally, it's between 90 and 99% efficient, which is still pretty good. But there's always going to be some energy that's lost to heat and friction and stuff like that. So as the charges are moving, creating friction, we lose some of it to heat. Now I've got a picture of a transformer here, and lost my train of thought here. Oh yeah. See if you can look at this and tell which type of transformer. Is it a step up or a step down? Well, if you look at this drawing, it says this is your primary voltage and your primary coil. So this one has more loops than the secondary. So it's going from more loops to less loops. So this is an example of a step down transformer. Now, electric companies, when they transmit our electrical power, they do so with really, really high voltages, but very low currents. The reason they do that is what I was mentioning before about the efficiency. We always have some power that's lost, and power is lost, there we go, to resistive heating in the wires. So the wires have a lot of resistance in it, which is going to oppose the motion of the current, and we get some of our power loss because it changes to heat. Now, power companies, when they generate the electrical power, they generate really, really high voltages, like several 100,000 volts, and then they send it out. And it goes out at the high voltages with very low current until it reaches the distributing station. They use step-down transformers to lower your voltage to about 20,000 volts. And then they send it out to businesses and homes and other places like that, where there is another transformer nearby that lowers your voltage again to 120 volts. Now again, each time the voltage is changing, your power is staying the same. So when we lower our voltage, we're actually increasing the current as well. Now, another use of transformers is in your cars. The ignition coil in your car is also a transformer. And what it does is it takes the 12 volts that you get from the battery and increases it to about 20,000 volts, which is enough to cause the spark plug to spark, and which in turn ignites the gas fumes in the engine. So when the gas ignites, it causes small combustion, which turns the pistons in your car, and everything goes from there. Now, one thing to know though is even though it does say DC here, you might want to write this down. Transformers only work with alternating current. Now it says DC here because the battery does provide direct current, but the transformer part, it's changed to alternating current because transformers really only work with alternating current. When we talked about ways you can induce current, we said that you can move a conductor in and out of a magnetic field. You can rotate a conductor within a magnetic field, or you can change the magnitude well, not necessarily the magnitude. If you change the magnetic field, you can induce current. So the only way we can get a changing magnetic field is with a changing current. Direct current doesn't change, it's one direction only. So it has to be alternating current for transformers to work. Now, transformer equation. This is basically a proportion. V2 over V1 equals N2 over N1. V2 is your secondary voltage, V1 is primary voltage. N2 is the number of loops or turns in your secondary coil, N1 is the number of turns in your primary coil. Now remember that the primary, the one on the bottom here and here, is the side that's hooked to the battery or generator. It's where you're getting the current from. It's your input side, what you start with. Secondary is your output side that it's changing into. Now another thing, remember that this is a proportion, and to solve a proportion you cross multiply and divide. So let's look at an example. Alright, so step-up transformer is used on a 120 volt line to provide a potential difference of 2400 volts. So my voltage started at 120, making that my primary, and ended at 2400 for my secondary. The primary has 75 turns. That's N1. What we're looking for is the number of turns the secondary has, so we want N2. So plug it into the formula. V2, 2400, over V1, 120, equals N2, which we don't know right now, over N1. Now technically proportions, there's more than one way you can set up a proportion as long as you're consistent on both sides of the equation. But regardless of how you end up setting it up, you should still, if done correctly, you should get the same answer either way. So in this one, I am going to multiply 2475 and then divide by 120. So cross multiply and divide. When I do that, I get 1500 turns. So another example. A step-up transformer is used to create a potential difference of 120,000 volts across the secondary. So this is V2. The potential difference across the primary is 117. So that's V1. The number of turns in the secondary is 25,500. So that's N2. And we're looking for the number of turns in the primary, which is N1. So set up the proportion. V2, 120,000, over V1, 117, equals N2, 25,500, over N1, which is what we're looking for. So now that the proportion is set up, we can solve, again, by cross-multiplying, multiply those two, and then divide by 120,000. Now, in this one, we get 24.9 about. But for the number of turns, we don't really want a decimal, we want a whole number answer. So we're going to round this to 25 turns. Now, I'm going to go ahead and include 24 in this one because it's something we've already covered. We've already talked about this in chapter 13. So I'm just going to go ahead and do the review on this. We're going to be talking about different types of electromagnetic waves and how it relates to what we're talking about in this chapter. Now, back in chapter 13, we learned that light is an electromagnetic wave because it's created when electric and magnetic fields rotate or oscillate, which oscillate means go back and forth over the same path again and again. They oscillate at 90 degrees to one another. They are perpendicular to one another. This makes EM waves, electromagnetic waves, transverse waves. Remember that a transverse wave is one whose particle, or in this case field motion, moves perpendicular to the wave motion. Now, there are 7 types of electromagnetic waves: radio, microwave, infrared, visible light, ultraviolet, X-rays, and gamma rays. Each of these 7 types of waves have its own frequency and wavelength, but in a vacuum they all travel at the same speed. That speed, remember, is 3 times 10 to the 8th meters per second. Now, the only light that we can see, the only ones that we're able to see of those is visible light. Those are colors. Roy G. Biv, if you remember, red, orange, yellow, green, blue, indigo, violet. But a lot of the time when scientists are studying radiation given off by different objects, what they'll do is they'll pick up the amount of radiation of that type, how much radiation is given off at different parts, and they'll kind of color code it. If you've ever seen thermal images of maybe a person or an animal or something like that, you'll notice that some parts, the hot parts, are kind of a red or a yellow or something like that. The cold parts are maybe purple or black. So we're not actually, that's not the actual infrared radiation, but they're kind of color coding how much was given off in different areas. So that's kind of what happens with other pictures like these. So light given off, let's say, from the sun. There's visible light that we can see, but there's also different types, and when they pick it up, they're able to translate it using visible light as the as what we're picking up. So here you can see that the red spots, and there's green and yellow and all that. That's different amounts of radio waves given off at those different locations. Now, the radio waves probably don't act, they're not actually red, yellow, and green and all that, but it's how we are translating it so we can understand it with our eyes. Okay. All right. Now, in the mid-1800s, a guy by the name of James Maxwell created several equations that describe the relationship between electric and magnetic fields. And among other things, his equations were used to make predictions, including that changing magnetic fields would create changing electric fields, which creates changing magnetic fields, and so on and so forth. So he basically predicted how electromagnetic waves would work. And this relates to what we're talking about in this chapter, because it's all this chapter 20 is about how you can use electricity to get magnets, or magnets to get electricity. And that's what's happening in an electromagnetic wave. One type is creating the next, which creates the next. Now, we've studied electric forces and magnetic forces in different chapters, but technically they are part of a single force. Electromagnetic force is one of the 4 fundamental forces in the universe. Those 4 forces being gravity, electromagnetic force, strong nuclear, and weak nuclear. Now, magnetic force, like gravitational and electric forces, obey an inverse square law, which tells us that the force is going to decrease as the distance increases. It's the flip and square stuff. For instance, if you double the distance between 2 magnetic poles, you're going to make the magnetic force between them only 1/4 as strong. Or let's say you brought them 3 times closer to so the distance was only 1/3 of what it was. When you bring them 3 times closer together, the force becomes 9 times stronger. Now, Other than the speed, another common feature between all electromagnetic waves is that they are all produced by accelerating charges. Because remember that moving charges is what creates a magnetic field. So as the charge is accelerated, it creates a changing magnetic field, which creates a changing electric field, which continues on as Maxwell predicted. Now, electromagnetic waves transfer their energy that's stored in the electric and magnetic fields as they rotate. And this energy transported by the EM waves is called electromagnetic radiation. So sometimes if you're looking up information about these, you might see electromagnetic waves, but other sites might use the phrase electromagnetic radiation. They are referring to the same thing. Now, an interesting thing about light, and actually all matter, is that they have properties that sometimes they act like waves, but other times they act like particles. And this is the dual nature of light. For example, we know light is a wave, but there's also something called a photon that is a particle of light. And the way we treat it is pretty much based on the energy. Low energy waves, like radio for instance, we would treat them more like waves, but high energy, like gamma radiation, would behave more like particles. Now, I mentioned a moment ago that all matter actually behaves this way. Most matter is too big for us to see it, but if you have something small like an electron, electrons are particles, but there are certain features of waves that we can see them exhibits. For instance, diffraction. Diffraction is when light bends around or through an obstacle. And electrons have been known to diffract. So they are particles, but exhibit wave-like properties under certain circumstances. All right. So going to talk briefly about the 7 types of electromagnetic waves. Radio is the longest wavelength and lowest energy. We use them a lot in communications, communicating information long distance, like with your cell phone or even just cable television. But another interesting fact is that objects in deep space have been known to emit radio waves as well. Microwaves, shorter wavelengths. We use them to study stars and talk with satellites in orbit. They're a little bit more useful because the smaller wavelengths are less likely to get distorted going through our atmosphere. We also use it in radar. So like police scanners and stuff like that to tell if you're speeding. They use a combination of microwaves and Doppler effect to tell whether you're speeding up, slowing down, how fast you're going. No. One sec here. There we go. Now, infrared is not visible to our eyes, but we can feel it. We can feel it as heat. Anything given off, that feels warm to us is giving off infrared radiation. We use it in remote controls for TVs or RC cars. Burglar alarms use it. Night vision goggles also use it. And an interesting fact is that mosquitoes can also see in infrared. I think I spelled that right. I'm actually not sure if I spelled that right. Oh well. Now, visible light is what we're able to see. Remember visible light, that's Roy G. Biv, our color spectrum. Red has the longest wavelength and lowest frequency. Violet is the shortest and highest frequency. And we can get visible light from many different sources. Incandescent light bulbs with a glowing filament, neon lights, typo there. Neon lights, when the gas inside the tubes have electricity going through them, they become excited and start to glow. Fluorescent lights are going to glow when exposed to high energy electrons or ultraviolet. We can also get light through chemical reactions like fireflies or anything with bioluminescence. They actually are caused glowing because of chemical reactions inside their bodies. And then the last 3, ultraviolet UV light is emitted by the sun and can cause sunburn. it's also linked to skin cancer. So careful with the tanning beds there. We also use it to kill bacteria and sterilize equipment, as well as to harden dental fillings. X-rays, many of us have had an X-ray in the past, if you've ever broken or fractured a bone before. So we use it in medicine for that. We also use it in airport security and in astrophysics as well, because some black holes have been known to give off X-ray radiation. Now, gamma rays have the shortest wavelengths and highest frequencies in energy, and these are produced by radioactive atoms and nuclear reactions. So anytime we have an unstable or radioactive atom, it tries to become more stable by giving off particles, and when it does that, what we get is gamma radiation. We also use this in cancer treatments. So it's not all bad. All right, that's it for chapter 20.